All right, this is lesson 7.6, exponential functions. We're going to learn how to evaluate and graph exponential functions. So let's just review functions quickly here. Circle each relation that is a function. This first one is not a function because it has two different outputs for the same input of 1. This one is a function. It has one output for each input. So is this one. This one obviously has many outputs for the same input of 5, so that's not a function. Cross out the equations that are not linear functions. This is not linear because you're not multiplying some number times x, you're dividing some number by x. This is a vertical line, so that's not a function. And this one is not a linear function, it's a quadratic function. All right, quick review of expressions here. In the expression 5 to the third 3 is an exponent. 3 to the x is an exponential expression. Match them up here. 3, the quantity 3n to the negative first power, that's the same as 1 over 3 to the n. 1/4 to the second power, that's the same as 4 to the negative second power. 2 over n to the third is the same as 8 over n to the third, and the quantity 5n to the negative second is the same as 1 over 25n to the second. All right. So a couple definitions here. An exponential function is a function of the form y equals a times b to the x, where a is not equal to 0, b is greater than 0, b is not equal to 1, and x is a real number. So all of the x values in the table, if you make a table of values for an exponential function, all of the x values will have a constant difference, and all of the y values have a constant ratio. So what that means is when you divide them, I'll just give a quick example. I want to write this down. This is an exponential function. Something like this, 10, 20, 40, 80, 160. What you will notice is if you take any number divided, any y value, output value divided by the previous output value, 160 divided by 80 equals 2. 80 divided by 40 equals 2. So any of these ratios, they always equal the same number. 20 divided by 10 is 2. So they have a constant ratio. All right, so let's look at some things and see if we can determine whether it's an exponential function or not. When you have a table of values, first check to make sure the x are going up by the same number. So we have a constant difference there. They are increasing by 1. And then we need a constant ratio in the y value. So we're just going to divide consecutive values in the table. So we're going to do 6 divided by 2, and that's 3. 10 divided by 6, that's 1.6 repeating, and 14 divided by 10 is 1.4. Then look at those values. If they're the same, it's exponential. If they're not, it's not exponential. So, and we can tell actually that we're adding 4 each time here. So this is a linear function, not an exponential. No, and we're going to say there is not a constant ratio. All right, the second one, this is an equation, and what we learned from the definition is we have to be able to write the equation like this, a times b to the x, where a is not equal to 0, and b is greater than 0, and b is not equal to 1. So we could change this to 1 times 2 to the x. Now a is not equal to 0. And b, so we got part of it, a is not equal to 0. And here b is greater than 0. We know 2 is greater than 0. And also we know b is not equal to 0. So this fits our description of an exponential function. So we're going to say yes on that one. All right. Go ahead, you can try it here with this problem. Check back with your answers. All right, suppose culture bacteria doubles each hour. There are initially 2,200 bacteria. The function f of x equals 2,200 times 2 to the x gives the number of bacteria after x hours. How many bacteria will there be after 5 hours? So all we really need to do is substitute 5 for x. And in function notation, what we're finding here is f of 5, 5 being the number of hours. And that's equal to 2,200 times 2 to the 5th power. So we're just substituting 5 for x. And order of operations, we need to do the power first, so that's 2,200 times 32, which is equal to 70,400. So there'll be 70,400 bacteria after 5 hours. All right, go ahead, you try it. All right, let's learn how to graph these exponential functions. I'm probably going to use my calculator a little to help me with this, but on this first one, the function is 0.25 times 3 to the x. So let's just check out some values for that. And on my calculator, so I'm going to just set this up, x, y, try some negative values, negative 3, negative 2, negative 1. And see what happens. So the function is 0.25 times 3 to the x. We'll start at negative 3. 0.25 times 3 caret. And we're going to put negative 3 for our power. Enter. Well, that's a really little number like 0.009. That's going to be hard to graph. Essentially, it's right down on the x-axis almost. If I go second, enter. Let's change that to a negative 2. Now we got 0.03. Second, enter, change it to negative 1. Try that again. There we go. We're still pretty close to 0. Second, enter, try 0 power. Now we're at 0.25. Try a positive power of 1. .75. 2. 2.25. 6.75. And you can see what I'm doing, but basically we're going to have these values to graph. Remember, this was like really a little values. Negative 2 was 0.03, 0.08, 0.25, 0.75, 2.25, 6.75, 20.25, and 60.75. So essentially I'm right down at 0 until I get to 0, then I'm at 0.25. We're just barely above there. 2.25, a little bit higher, 6.75 on, oops, that's on number 3. So that'd be more like that. Then on 4, we're at 20.25, and then at 5, we're at 60.75. So, and now I'm just going to draw a curve because we could have any real number be a solution here. And remember, it went down close to 0. So this, one thing I know too, it'll never actually hit 0. So it just kind of crawls right along the x-axis there. So get some values. Plot those values. Again, we have some really low values here, really close to the x-axis, 1/18, 1/6, 1/2, and then at 1, finally we're at 3/2, which is right there, so we can kind of see a curve going like, maybe we should do one more, let's do 2. So 3 to the second is 9. So we got half times 9, and that's 4.5. So we can get one more value at 2 is 4.5, so that's right there. So there's our curve. All right, we're going to graph another one here. Now these are kind of tricky because the values get big so fast. But basically we need to get a few years. Now this says, this represents 12-year period, so this is actually 12 years, 24 years, and so on, 36 years. So, but we're going to make a table of values here again, x and f of x. And if we put 0 in here for x, so do 2 to the 0, we're going to get 7,500. If we put 1 in, we're going to get 15,000. 2, we're going to get 30,000. And notice it's doubling, which makes sense because we're multiplying by 2. So the next one is 60,000. Next one is 120,000. Next one is 240,000. And so on. The last one is 480,000. If I'm going to fit that on here, I have to think about that scale. I can use this 48 as long as I multiply these values by 10,000. So at 0, I'm going to be at less than 1. It's like 3/4 of 10,000. So way down here. At 1, I'm going to be at 1.5 10,000s. At 2, I'm going to be at 3 10,000s. At 3, I'm going to be at 60. At 6 10,000s. At 4, I'm going to be at 12 10,000s. At 5, I'll be at 24. And then at 6, I'll be at 48. And then we'll just draw a smooth curve because our value is going to continue to grow. Right? Good, you try that. Check back with your answers. And your graph should look something like that. All right. Lesson check is this function, is this an exponential function? According to our rules, if we can write it like this, it's an exponential function as long as a and b are good. And b, the restrictions are b cannot equal 1 and b has to be greater than 0. So our b is -2 in this exponential function. Our a is actually 1 times -2, but b has to be greater than 0, so it is not, because we can just say b is less than 0. And that's because b is equal to -2 in this case. All right, that's it. We'll see you tomorrow.